Okay, our final talk is from Junho Su, and it's on the P4OVN offload pipeline.
Hello everyone, my name is Juno Seo, working for Intel. My role in Intel is to design and build the cloud networking infrastructure for Intel Tiber AI Cloud. Intel Tiber AI Cloud is a public cloud service launched in September 2023 and give customer access to the latest Intel hardware and software to test out by bringing their AI workload before going to market without burden on capex investment. Previously, we built tenants network on top of enterprise network. To isolate network between tenants networks, we rely on VLAN and VXLAN from vendor switches hardware, leading us to relatively static configuration audited by a company authority, not by tenants. It not only limits us the scale of networks, but also reduces agility for cloud service by introducing long provisioning time when new configuration changes are requested from tenants, even simple changes in its configuration. Because various stakeholders are involved in reviewing the changes to analyze how much the impact on enterprise network from the security perspective. This new requirement of decoupling tenants network from the provider enterprise network lead us to consider Intel Smart 8 called IPU. In this talk, I'm going to talk about how we address this problem with Intel IPU. First, I'm going to cover briefly introduction to Intel IPU, and then quick overview of P4OVN, which is the open pipeline implementation in P4 language for IPU. And then I will be digging into a whole P4 pipeline implementation to run open pipeline in IPU. Before jumping into main topic today, let me briefly introduce what Intel IPU is. Basically, IPU is a smart NIC. In IPU, there is ASIC, which is consisting of two main components. First one is network subsystem on the left-hand side of the picture. Another is compute complex subsystem on the right-hand side of the picture. In the middle, there are three protocol engines, RDMA, NVMe, and RAN. But in our use case, we currently only use RAN protocol engine to transmit and receive packets from two hosts or IPU compute complex through DMA. Down below, there is a packet processing pipeline we also call FXP to do packet manipulation. It is P4 programmable pipeline, and today P4 oven pipeline is implemented in this hardware component. Packets are normally flowing from north to south or vice versa, or from host to Ethernet port, or from Ethernet port to host. Optionally, packets can be redirected to ARM Compute Complex Subsystem called ACC, and then do full packet processing with 16 ARM cores. Furthermore, since it comes with a Linux net distribution, you can run any types of application like control plane function or monitoring function. Therefore, ACC can be used for not only data plane paths, but also control plane paths. On the right bottom, IPU has a separate isolate and secure management subsystem called IMC. It is quite similar as BMC in host board management, but it is more specialized to IPU device management. For example, power on reset, clock and power control of the device itself, it do the network subsystem initialization. As part of this initialization, it do PCI initialization and resource management in IPU FXP. Okay, so what is the P4 oven? P4 oven is a co-design of IPU hardware and software to offload oven pipeline into off-path SmartNIC, IPU. The goal of P4 oven is to use IPU FXP as much as possible to forward packet in hardware. Normally, layer 2 and lower layer 3 forwarding tables in open pipeline can be relatively easy to offload and implement in hardware than any other tables that require statefulness because of its stateless characteristic, which means no relationship between a current packet and the following subsequent packet, and its simplicity in actions applies to packets like output to a certain port or modify packet headers. But in Oven, it requires more than layer 2 and layer 3 forwarding in Oven pipeline. It has such stateful packet processing table during its pipeline. For example, the stateful ACL, normally it is used to implement security groups or distributed firewall, and a stateful load balancer to distribute traffic into sticky sessions once they are established, and stateful NOT to translate one address space to another address space for sessions. All these three use cases require a connection tracking to keep maintaining sessions, which means the relationship between the first packet and the subsequent packet of flow. To do this, normally it is implemented in software data paths, for example, the Linux IP tables or IPVS, not in hardware due to hardware resource constraint. In terms of ticket memory size in a single die and increasing complexity in hardware design to implement a state machine for connection tracking. And hardware implementation is not flexible. To deal with such a cases, P4OVN delegate stateful packet processing to IPU ACC, on which OVS software data path runs, if hardware alone is unable to process. Our approach is that every first packet of flows is pumped to IPU ACC by looking up the flow table and go through the open pipeline in OVS software data path. As a result of packet processing by open pipeline, it determines whether a flow is accepted or not. If accepted, the flow is offloaded in the flow table in IPU FXP via the data plane. Otherwise, it is dropped by OVS. Any subsequent packet of the flow will look up this flow table in hardware first, and then if the flow table hit only hardware forwarding pipeline implementing L2 L3 forwarding behavior is executed to determine the phase of the packet. As I mentioned in the previous slide, every first packet of flow or missed packets are pumped to IPU ACC, and OVS software data paths running on IPU ACC execute a full oven pipeline packet processing, not only do stateless layer to layer 3 forwarding, but also do stateful ACL load balancer NOT functionality. And once it is determined to forward the packet to target port, the flow is offloaded into the flow table cache from OVS software data path. The flow table in IPU FXP is 5-tuple flow header based table having only two actions like accept or deny. Unlike any other P4 table, this table has a special ability, which is capable of entry insertions via data plane. Moreover, it is capable of timer-based entry expiration and eviction if the entries are no longer being used to lookup. In this way, P4OVN achieves table insertion and line rate for flow table caching in hardware, which is compared with the table programming via control plane like a P4 runtime API on the right-hand side. Let's take a more deeply look at our P4 implementation for Oven pipeline, which is offloaded in IPU FXP. In P4OVN, as I mentioned earlier, we have decided to offload a subset of logical flow tables defined in Oven pipeline into IPU hardware FXP. The first target was to offload layer 2, layer 3 logical flow tables into IPU FXP in P4 pipeline. On the left-hand side of the picture, it roughly highlights the current Oven pipeline implementation. Basically, Oven logical data path consists of logical switch pipeline and logical router pipeline. And the pipelines have ingress and egress pipeline each. And theoretically, Oven software data path allows series of logical switches and logical router daisy chain with each other. But in our design, we restrict this freedom by allowing just one logical router per tenant. And under this logical router, a tenant can create logical switches as many as they want. So that with this restriction, we achieve is to offload over layer 2, layer 3 forwarding pipeline into IPU FXP hardware in P4. In layer 2 forwarding, when a packet comes in the ingress switch pipeline, it first look up the physical to logical mapping table to find the logical data path ID that this packet belongs to, and then go through the stateful ACL load balancer NOT tables, and then finally goes to the L2 lookup table here to find a destination location or port. At this point, there are two possibilities where the destination port is located in the same chassis that the source port is located, or is located in the different chassis. In this case, it needs a Geneva encapsulation to pass an original packet to the remote chassis through layer 3 underlay network, and then do the rest of the egress logical switch pipeline in the different chassis. So it executes the egress logical switch pipeline depends on the location of the destination port. Layer 3 forwarding is working in quite different way. All the ingress logical router pipeline and the egress router pipeline are executed in the same source chassis, and then finally do go through the ingress switch pipeline. As described earlier, depending on the location of the target output port, the egress logical switch pipeline is executed either in the same chassis or in the different chassis. We do the similar packet processing in hardware. As you can see on the right-hand side, IPU FXP physically split into three passes. One is TX pass, where packet comes down either from host or from IPU ACC and go through FXP and then go to the Ethernet physical port. Another pass is RX pass, where packets are arrived on Ethernet physical port and then through FXP and then go up to either host or IPU ACC. The third pass is a loopback pass for TX packet that need to be turned around back to RX pass. When a packet comes in from host in a TX path, it first looks up the physical to logical mapping table, which maps the physical port ID that the packet comes in to the logical data path ID of the logical switch data path ID that this physical port is bind with. And in parallel, it looks up the router interface MAC address table to decide whether layer 2 switching or layer 3 routing lookup in the next stage. If it is a layer 2 switching, next it look up the L24 TX table to find the logical output port to which this packet is delivered. At this point, if this logical output port is located in the same IPU or chassis, the packet turn around through the loopback port and then look up the L24 RX table to find the actual physical port that this logical output port is bind with. In case of the logical output port is located in a different IPU or chassis, next it goes through the Zenith incap table and then finally goes to the physical port. Once the Zenith packet is arrived on the remote IPU physical port, then it is delivered to the actual physical output port after Zenith decap table and L24 RX table lookup. In case of layer 3 routing, when the router interface MAC table is hit, the packet first look up the IPv4 LPM table to find a next neighbor logical switch, and then look up the AIP table to find the MAC address of the logical output port to be which is to be written in the destination MAC address field in either header of the original packet along with the source MAC address of the logical router interface, and then do the same packet processing execution as layer 2 packet processing, but with a different logical switch context or data path ID. As you can see in this figure, the layer 2 and layer 3 tables in open pipeline are mapped to the P4 table in the same color. For example, the uh, uh, ls in L2 lookup table is mapped to three table, which are a router interface MAC table and L24 TX table and L24 ARC table, and they have been populated with the same entries in the ls in L2 lookup table of open pipeline by an open controller. In the previous slide, I was explaining a baseline P4 pipeline implementation for layer 2 layer 3 flow tables in open pipeline offloaded into IPU hardware FXP. Now I'm going to explain flow punting scenario for the first packet of flows to do a stateful packet processing in OVN software data path in IPU ACC. As I explained earlier, every first packet of flow are pumped to IPU ACC by flow table lookup here. Even though a packet is processed by a layer 2, layer 3 relay tables, and the face of the packet has been made before the flow table lookup, the first packet is always a miss on this flow table, then it overrides the actions that has been made in the previous tables to point to the port to which IPU ACC is connected to. Then this first packet is looped back to the RX path and is forwarded to the certain port to which IPU ACC is connected. Then OBS here receive the packet and execute a full open pipeline and determine the logical output port, and then the packet is re-injected into the TX packs again. At this point, since the full packet processing is done by open pipeline in OVS, the packet doesn't need to do a reprocess again through the layer 2 and layer 3 table in IPU FXP in here. Further, the logical output port of this packet has been determined already by OVS software data path. So the packet type could be either the original packet or the Geneva in-cap packet, depending on the location of the logical output port. If the logical output port is located in the same chassis, then original packet is re-injected into the IPU FXP and then directly loop back from ACC table to the from the ACC table here to the table in the RX path, and then is forwarded to the actual physical port after L24 RX table lookup. If the logical output port is located in a different chassis, then the ZNIB packet is re-injected into the IPU FXP, and then it goes straight down to the Ethernet port here. The flow table has a as I mentioned earlier, the flow table has a special capability than the other tables. Table insertion can be done with a data packet via data plane, not via control plane. Further, the inserted entries are automatically evicted after a timeout if not used later. Now the subsequent packet of flow are hit only by these hardware tables and then are forwarded only by the IPU hub FXP here. So far, we have discussed the open pipeline and P4 pipeline for compute node, which means the communication in logical networks happening between two workloads running on this compute node. Sometimes these workloads need connectivity to physical networks. In open architecture, open delegate this type of connectivity to physical networks through gateway node dedicated to some chassis other than the compute node. The main use case of gateway node is many-to-one NOT. To redirect traffic to a dedicated gateway chassis, Open introduced a new table called error in gateway redirect table in here, which is colored in light blue box during the ingress router pipeline processing in open pipeline. Once it hit, a packet is immediately encapsulated by the ZNIP header and passed over to the gateway chassis specified in the table. And then once the packet is arrived on the gateway redirect chassis, then it executes the rest of the egress logical router pipeline and the ingress and egress logical switch pipeline on that chassis, like this. In the same way, in P4 pipeline, this gateway redirect table is also mapped into the same table in IPU ApexP after IPv4 LPM lookup. Once it hit, the rest of the packet processing pipeline described earlier are executed by OVS software data paths running on the gateway node, which is same as the open pipeline running on the OVS. Now let's take a look at the demo. In summary, today I have covered our P4 pipeline implementation to offload open pipeline into both IPU software and hardware for Intel Tiber AI cloud networking. In summary, P4OVN is capable of layer 2, layer 3 forwarding in IPU FXP hardware and working with the OVS running on IPU ACC to run the full OVN pipeline. Finally, it is capable of centralized and distributed gateway functionality. Thanks for listening.
Okay, I don't believe the speaker is online at the moment. Yeah. Okay. Hold on. No. Okay. So I guess if you do have any questions, the speaker's email address is in the presentation. So go ahead and